So consider these three functions. All right, and what I'd like to do is think about analytically continuing outside of the disk of convergence of each of these functions. So what is the disk of convergence of each of these functions? Well, let's see. Let's look at the first one. We know that 1 over the radius of convergence is equal to the limit superior of a root of the coefficients. Okay? So I'm going to do lim sup of, here, the coefficient 1 over 2 to the n is the coefficient of z to the 2 to the n. So I need to take the 2 to the nth root of 1 over 2 to the n. So that's the limit superior of 2 to the minus n over 2 to the n. Now it should be pretty clear that as n tends to infinity, 2 to the n beats n. It beats it rather badly. All right? So for this reason, 1 over the radius of convergence is equal to 1. So this expansion, converges on the disk modulus z less than 1. All right? How about this one? 1 over r. Lim sup, it's the 2 to the nth root of 1 over 3 to the n. So I've got the limit superior of 3 to the minus n over 2 to the n. As n goes to infinity, once again, 2 to the n beats n. This becomes 3 to the 0, which is 1. So this converges on the same disk of convergence. All right? How about this one? All right, So all three of these series have the same disk of convergence. Now let's go ahead and look at what these functions look like on a circle of convergence. So I've got, I'm going to call them f1 of z equal to the sum of z to the 2 to the n over 2 to the n, and I'm going to sum from 0 till, let's go up to 12. Okay? And then I'm going to have f2 and f3. All right, this was z to the 2 to the n divided by 2 to the n squared. This was divided by 3 to the n. And I need f2. All right? And now I'm going to plot. Let's do real part, and this is parametric plot. Real part of f1 of z, imaginary part of f1 of z, and I'm going to replace z with e to the it. And I'm going to plot this from 0 to 2 pi. All right, so, and let me plot a lot of points. I'm going to plot 200 points. All right, and this is what we get. This is this kind of fractal pattern. We can see, in fact, if we zoom in on part of it, all right, now that doesn't look fractal, but remember that I only summed up to 12. Let's sum up to 20 and see what happens now. Now it's a bit more iffy, all right? And what we can see, we go out a little bit, it gets a little crazy around there, all right? Go out a little bit more, show me a little bit more of it, all right? This one wasn't a terrible one, but the reason why it's not differentiable anywhere there is because if I imagine taking a derivative with respect to z, I would get 2 to the n, z to the 2 to the n minus 1 divided by 2 to the n. All right? If I want to make it really crazy, I can change it like this. By the way, this won't change the disk of convergence. But if I make it z to the 3 to the n, now it's going to get a bit crazier. Notice that that was just pi over 2 minus 0.1 to pi over 2 plus 0.1. We can look at the whole range here. And what we find is that it's a pretty crazy graph. Notice that here, if I try to take a derivative, I would get 3 to the n, z to the 3 to the n minus 1 divided by 2 to the n. Not only does that not converge anywhere where the modulus of z equals 1, but it actually goes to infinity. Really bad there. All right, now let's look at F2. F2 was z to the 2 to the n over 3 to the n. So if I try to take a derivative, I would get 2 to the n over 3 to the n, z to the 2 to the n minus 1. So this one will converge fine, and its derivative will converge. And let's see what this looks like. Oh, you have to change it in both places. All right, this one is much better behaved. So you can see that this one is smooth. If I was to plot over a small region, it's smooth. It's differentiable, no problem. It doesn't have a second derivative that works well, but it's differentiable, no problem. What about F3? F3 no problem at all. Okay? So this was the behavior of these three functions. Really, we looked at 4 of them, all right, on the circle of convergence. Now, they all have the same circle of convergence. And in fact, if you look, when the modulus of z equals 1, this function, and of course you could do the same thing with these other two, and also with the z to the 3 to the n that I showed the graph of, all those functions converge absolutely on the disk of convergence. Converge absolutely. This function doesn't have, like, its derivative doesn't converge on, at least not absolutely, on the circle of convergence. This function, if you take its derivative, you would get this function. That converges absolutely on z equals 1 in modulus. If I take a second derivative, though, then I'll get like 4 to the n over 3 to the n, and I'll get an absolutely divergent series. All right? But how about this one? This one, if I take its derivative, I get that. If I take the next derivative, I would get effectively that. That converges too. If I take its third derivative, I get that. If I take its kth derivative, I get that. K is fixed. All of these are absolutely convergent on the circle. Okay? So we've got 3 functions, 4 if you include the z to the 3 to the n, that all have the same disk of convergence. All of them converge absolutely on their circle of convergence. This one has a derivative that does not converge absolutely on the circle of convergence. This one has a derivative that converges absolutely on the circle of convergence, but its second derivative doesn't. This one sees it and all of its derivatives converge absolutely on the circle of convergence. Very different behavior on the circle of convergence. Despite that fact, all of them have the same circle of convergence. That means every single one of these functions must have at least one singular point on the circle of convergence. All right? Now, what Pringsheim told us is that in a direction in which all the contributions past a certain point to the series have the same argument, where they're all lining up, there's no cancellations, the function can't behave any worse than that. So since you have to have a singular point in at least one direction, a direction in which all of the arguments of the terms that you're adding are the same, has to be singular. All right? So let's see what that means here. Suppose that I had a direction t equals 5 pi over 4. So that's here. I went in that direction. Okay? Now, in that direction, I would have e to the I 5 pi over 4. For all of these functions, I'm doing z to the 2 to the n. Okay? So when n equals 0, it's e to the I 5 pi over 4. When n equals 1, it's e to the I 5 pi over 2. When n equals 2, it's e to the I 5 pi. All those have different arguments, so they can allow for cancellations. But what happens when n equals 3? when n equals 3, I would have e to the I 10 pi. The argument of that is 0. What about when n equals 4? Well, now I have e to the I 20 pi. The argument of that is 0. What about when n equals 5? The argument of that is 0. All n's greater than 2. See, the argument of z to the 2 to the n in this direction just be 0. The coefficients are all positive real numbers, and that means that this direction must lead to a singular point. All right? If you think carefully about that, you see that that same argument can be made for 3 pi over 4, and for pi over 4, and for 7 pi over 4. You'll also see that that argument can be made for pi over 2, 3 pi over 2, pi. Clearly, it can be made for 0. It can also be made for pi over 8, 3 pi over 8, 5 pi over 8, 7 pi over 8. It can be made, in fact, for any number pi over some power of 2. And so, for that reason, we see that in the neighborhood of any point on this circle, there must be points in the neighborhood, in any neighborhood of that point, that have an argument that can be written like that for some number and some value of k. All right? Because there's just too many, right? If I wanted something near 0.3, like 3/10, I can certainly get an approximation to that, to 3/10, with a denominator that's a power of 2. All right, and I can get arbitrarily close. All right, or I guess I would have to do 3/10 divided by pi. But that's fine too. We can do that. That's going to be a decimal, and you can get as close as you want to that with a denominator that's a power of 2. So for that reason, there are points in every neighborhood of this point that have to be singular points. So that means that point must also be a singular point. So for all of these functions, the whole circle of convergence consists of singular points. None of these functions can be analytically continued outside of the disk of convergence, modulus z less than 1. The circle of convergence is said to be a domain wall for this reason. This is despite the fact that this function and all of its derivatives converge absolutely on the circle of convergence. Despite that fact, this function is demonstrably singular at every single point on its circle of convergence, right? So from that, we see that the behavior on the circle of convergence is decidedly varied, all right?